Well, I missed the Nobel Prize.
12 months, 12 labs, one source to unite
Right.
them all. Hi everyone, my name is Pranoti. I'm your host of Under the Microscope. I'm very excited to introduce you to today's guest, Armando Rastelli, professor at the Institute of Semiconductor and Solid State Physics at the Johannes Kepler University Linz in Austria. So, welcome, Armando. Lovely to have you on Under the Microscope. How far is Linz from Vienna? Because I think most people know Vienna.
Yeah, it's about 200 kilometers.
Oh, that's quite far.
There's,
Okay.
there's a very good train connections.
Armando, please tell me about your research. What exactly are you doing in Linz, which is 200 kilometers from Vienna? So, what is your research? I know it is something with quantum dots, but please explain. What exactly are you doing?
Yes, we are working with these tiny objects which are quantum dots, and just to understand, so you can imagine this as a quantum dot, or maybe you can take it as a chocolate chip in a muffin, and if it would be really as big as a chocolate chip in a muffin, then the muffin would have a diameter of about 5 kilometers. So it would take you about one hour to walk from one side to another. So very, very small. And they are made of special materials, which are semiconductors. These are the materials which are inside your mobile, your TV, your computer, and so on. And what we are doing is that we make these quantum dots, we make a special class of these quantum dots, and then we study their properties, and we try to see if they are good for some special applications.
Okay, while you're telling me this, I'm imagining a cookie and I'm drawing it out. And as I'm drinking a coffee as well, it's now I have to get a chocolate chip cookie. Okay, so 5 kilometer. Let's go with that, right? 5 kilometer. Oh, that's a really big chocolate chip cookie. I would love. Okay, focus. And the quantum dot is like a. So that is to understand the scale, right? The dimensions at which we are working on. So, how big are these quantum dots? Like, how big, like in reality?
Yeah. The typical size is of about 50 nanometers.
So that's basically 5 multiplied by 10 to the power minus 10. So like angstrom, if that's what the listeners understand. So 5 angstrom.
Well, it's 500 angstrom. 500.
500. Sorry. Of course. Yeah, 500 angstrom. Wow. See, I need a chocolate chip cookie to do all these calculations in my mind. That is brilliant. That is brilliant. And what are the shapes of these quantum dots? Are they always like the table tennis ball that you showed me, or like?
Well, actually, the dots we are dealing with are like squeezed balls, so maybe a flat object. You can imagine like a lens or, as I said, a chocolate chip maybe. So maybe that's a diameter of about 50 nanometers and the height of 7 nanometers. So a ratio between width to height of about 10.
Ah, okay. So it's not like a sphere. It's more like a. It's more
bump.
like
a small bump.
It's a bump.
Or something like an object like this, or top of, flat on top and a bump below.
Or if you just take like a sphere and you cut it like somewhere in the
like
half or
exactly,
at some point,
yeah.
so it's a slice.
Yes, exactly. Yeah.
It's a sliced. Okay.
Yes.
Okay. So you make these you and your group, of course.
Yes,
you make these quantum dots. Yeah. Okay. And what do you do with it? Like, okay, you made the quantum dots, which are not chocolate chips in the chocolate, but why do you do this? Why do we need this?
Yeah, well, first of all, we have special ovens to cook these quantum dots. Of course, it's not like muffins. Why we do that? Because the behavior of these structures is very special. So just to illustrate it, so the optical properties of these quantum dots depend on size. So if you take a quantum dot which is small, then its color tends to go towards the blue, while a big quantum dot has a color which tends to go to the red. That's what happens when sizes get small, and then there are many special properties of these quantum dots which can be described by quantum mechanics. We want to understand better these properties and to take profit of them. maybe for some technological application.
This is amazing. Okay, so if we take, let's say, a cookie, depending on where we cut it, that will define how big the size is. That's not how it is made, of course, but just for visualization purposes. And then the smaller it is, the bluer.
Yeah, I made the example with color, but now if you are sticking to the example of a cookie, is like when you start slicing it, the taste changes, and maybe you can decide the size where it tastes the better.
Ooh, oh, that is cool. That I like. Haha.
Or maybe
that
you
I like.
cutting your piece of chocolate at the beginning is not very sweet, and then when you cut it, it gets sweeter, and then you stop cutting, and then you say, okay, this is the right size. I like.
This is what I want. This is my application.
Yeah, exactly.
Aha. Okay. So when you say size, what dimensions are we talking?
Yeah, that depends also on the materials we are considering. So if for our quantum dots, we could go from sizes which are just 1 nanometer tall up to maybe 15, 20 nanometers. At some point, if the size is too big, then we don't have big changes when we move from large size, or we lose the cool properties of these quantum dots. They're not so quantum anymore. And so there is a certain range, which is of the order of a few nanometers up to a few tenths of nanometers.
Okay, yeah, no, that makes sense. That makes a lot of sense. So the magic happens in the nano range, and the bigger it gets, the more it's like, yeah, whatever.
Normal.
It's just that.
Let's say macro and normal words, we understand everything. And
the basic stuff,
yes,
which everyone knows.
Yes.
There's no fun in that, of course. When you say the size of the quantum dot, when you say like 10 nanometer, 2 nanometers, which is the height of this bump, so to say. So is it always that everyone is reporting the height? So when someone says we created quantum dots, which are, I don't know, 30 nanometer or so, it's always the height, right? Not the spread.
Well, I should be precise that there are actually two major classes of quantum dots. And the quantum dots one hears the most, actually, they are colloidal quantum dots, and they are almost spherical. So these are the quantum dots which are already, actually they were awarded, or the discoverers of these quantum dots were awarded the Nobel Prize just last year.
So your quantum dots are the ones that are these bumps.
The technical word is, so for the first ones, the round ones, they are called colloidal quantum dots, and they find already applications, for instance, in brilliant TV screens. And our quantum dots are called epitaxial quantum dots. They are more suitable for optoelectronic devices, and they are flat usually, or kind of bumps.
Flattish, like bumpy.
Yeah.
Okay.
Yeah.
Oh, okay. Epitaxial quantum dots. Okay. Epitaxial quantum dots, which are interesting.
And the others were the colloidal.
The colloidal ones. Okay. And the colloidal ones are like the LCD screen or whatever the screens to make the screens better or more clear. And the epitaxial quantum dots are for optoelectronic properties.
So, for instance, they are interesting for lasers or novel sources of quantum light, like what we have for the Quantour project.
For the Quantour project with the lasers, or for the single photon emission and stuff. With the colloidal quantum dots, you already gave an example that, like with our TV screens, and that is their application. But about the epitaxial quantum dots, can you give me a real life example of where we might already have it, or we can have it if we don't have it already?
These are applications which are still kind of classical. So they belong to the first quantum revolution, where quantum mechanics made a difference the first time. So all what we have, so like the chips or the LEDs, lasers, these belong to the inventions or discoveries which belong to the so-called first quantum revolution. So now these quantum dots, the epitaxial quantum dots, could make a difference also for the second quantum revolution, where we want to use the more delicate and more fragile properties of quantum mechanical systems. And one particular application is in secure communication, where you want to encrypt your messages in an absolutely secure way. And there, one of the approaches is to try to create secure keys using properties of single photons. And that's what we try to do, and we and many other groups in the world. is to, first of all, to have sources of single photons or entangled photons. And use these photons or things you can, information which you can store in these photons to create and to distribute secure keys with which you can encrypt messages.
Now it is starting to form a story in my mind as well, because what Doris spoke about, what Toby spoke about as well with the secure communication. And for the listeners or the watchers, I would highly recommend you to pause at this point, maybe go back to Doris Writer's episode and Toby's episode, where they also talk about. So Doris approaches it from a theoretical perspective, and Toby is approaching it from an experimental perspective, just like Armando, where they also talk about the secure communication with quantum. If you are following the quantor.eu Instagram, you would get the jokes now why there is the quantum security jacket person who is going around with the suitcase. You will understand that. So for the Quantor project, right, the source that you have at the moment with you, that one has circular rings, right? It has circular rings. So now help me understand this. So your quantum dots, which are epitaxial, which are these bumps, uh, how do they combine?
Yeah, that's a very good question. So essentially, you have a quantum dot, and this is a, for instance, if you are using it as a source of light, you have to imagine that this light is emitted by the quantum dot. But usually, if you don't do anything, the quantum dot emits light in all directions.
Right.
And imagine you want to collect light either with your eyes or actually in practice through an optical fiber. So you want to have light to be directed in a specific direction.
Right.
And those rings you are referring to are exactly for this purpose, to make sure that light which would be lost in this direction, for instance, is redirected towards your direction. So that's the idea. Actually, there is a mirror behind the quantum dot, so that all light which is coming towards me is also redirected in your direction. And also these rings make sure that all the light, or maybe 90% of the light which is emitted, comes to your direction. And these rings are much bigger actually than the quantum dot itself. You have, I said, so the quantum dot could be maybe 14 nanometers big, and the disk where it is embedded is about 10 times bigger. And then these rings are or one order of magnitude larger. So we are talking about a structure which has a footprint of a few micrometers, 100 times bigger than the quantum dot itself. The source is very tiny, and around there is a big thing. But this is similar to what we have for LEDs, for instance, light emitting diodes. If you look at the chip inside the LED, it's very small, and to make sure that light comes towards you, there is a lens in front. So these rings are a kind of very specialized lens with very, very high efficiency, because we want to collect single photons, and we want to have all of them. You cannot afford any loss. For an LED, you are happy with a simple lens. For a single photon source, you want to have a very special lens which makes sure that you get all light where you want.
Oh, that is so cool. I think I'm going to be a pro after interviewing all of you Quantor heroes.
Yes, I'm sure.
At the end of it, I would be like, okay, just ask me anything. I know everything. Colloidal quantum dots, epitaxial quantum dots, secure communication, why are the rings, what's with the bumps and everything. Oh, I'm going to be a pro.
And then we send the students to you to learn. Because you are collecting the information from all the groups, from many groups in Europe about the topic.
Exactly. 12 months, 12 labs, one source to unite them all. And Toby and Doris never let me use the unite them all, because they're like, that's too dramatic. No, don't do that. I'm like, well, we need the drama.
Why not?
Yeah, thank you, Armando.
It's nice. I support you.
Thank you. I'm okay, on record now, Toby and Doris, I know you're gonna watch this and you're gonna listen to this episode. I have Armando on record, one source to unite them.
Yes. Or maybe we could say that at the end you will get entangled with all of us.
Ooh.
So we will distribute entanglement for Europe.
Ooh.
Okay, don't take me too seriously.
I love that. I love that.
Entanglement is something fragile, but who knows?
Yeah, true. I will be the entangle. No. Okay. We can do so many things here but we will have fun with it for sure. But this is great. This is really cool. So Armando, tell me, I'm always curious. How did this happen? Was a 5-year-old or a 10-year-old Armando thinking that, yeah, I'm going to be a professor in Linz in Austria? Give me some time. Just give me a few years and a few decades, and I will do it. How did you end up becoming a professor at the University of Linz or the university in Linz, leading a group, being a professor? How did that happen? Tell me about your career journey.
Okay, since you mentioned the young age, I liked very much playing and dismounting all the technological equipment I had at home, and I thought I would become an electrical technician. Then, at some point, at the age of maybe 16, I discovered something like physics. I said, "Oh, this is really cool." And I want to do that. So I studied physics. I made my thesis work, my master's thesis. It was called Laurea in Italy, underground lab, which is a tunnel under a mountain. So it's about 1.5 kilometers below the top of the mountain. We would collect high energy particles coming from the space, muons and neutrinos and stuff like that. So I was working there, and it sounds very fascinating, but in practice, for a physicist, there's not much to do, or you don't have so much freedom to try out things which come to your mind, because the experiments are very, very big. So then I switched during my PhD to solid state physics and semiconductor physics, and then got my PhD in Italy, and working also at the ETH at Zurich in Switzerland. Then I was also in Finland for some time. For 3 months, and then I moved to Stuttgart, to Germany, and my career path went to Dresden, to Germany, until 2012. And then 2012, I got a professorship here in Linz, where I could build up my own group, and I'm here.
Okay.
It's kind of random work.
Yeah, it's quite an unusual path. I still have so many questions about the master thesis in the tunnel. So you mentioned there were the materials from space during your master time.
Well, high energy particles.
High energy particles. Okay.
Yeah. It's a cosmic rays, are called.
Okay. These are not UFOs that you're talking about.
No. It's just very tiny point-like particles, even much smaller than quantum dots, so even smaller than atoms. So it's
So what do? You go into the mountain in the tunnel and you just grab some sand or some soil?
no,
What?
no. They are coming. So you have very specialized detectors with very big area. So you need many square meters of detectors, or tens or hundreds of square meters of detectors, or cubic meters, or thousands of cubic meters of detectors. And then you wait. You just wait that some particle comes from space, and it has enough energy to cross the full mountain, or it has weak interaction with rock. And then you collect these particles and look at their properties, you look at their energy, their direction, and so on.
Okay, now I understand what you mean when you say that it sounds super fancy, but in reality, that
It's just a matter of waiting and discriminating this particle for something, or looking what is interesting. So many things are just known, and the exotic things which are not known are very rare. So it may take you decades of waiting, and maybe you don't find anything which is interesting.
Yeah.
And there's a very high potential for frustration at some point.
Sometimes you don't find anything for decades, and sometimes you find something.
Yes.
Okay. You started in Italy, then you went to Zurich, so in Switzerland. Then you went to Finland.
Yes, to Tampere.
To the Tampere in Finland. Then you went to Stuttgart in Germany. Were you at the Max Planck in Stuttgart?
Yes.
Really?
Yes. Max Planck Institute. Forschung.
So you were at the Max Planck in Stuttgart. That's where I did my master's. I was there for 3 years, between 12 to 15.
Really? Cool.
Yes.
Okay. I was already gone.
Were you also in Fauke's department, von Klitzing?
Yes.
Really? No way. When were you in Stuttgart?
It was a subgroup of.
Which one? There were two. Which one were you?
It was already gone when you came, because it was Oliver Schmidt. It was my boss. It was a Epitaxial group. It was, I think it was shut down.
Okay. Yeah, no. I came in 2012, end of 2012. I think by then you had moved on.
Yes. I had left in 2007, so 5 years
Okay,
earlier.
but we have that connection then with Southeast
Very interesting,
thing.
yes.
That is,
Many people make a stop at Max Planck Institute.
yeah, very,
It's very good
yeah,
place, yeah.
it's really cool. So then after Stuttgart, you were in Dresden, in Germany.
Yeah,
Which institute? Because there are like 50 zillion.
it was the Leibniz
The
Institute,
Leibniz
IFW.
IFW. Okay. Because they have IFW and IPF as well, I think, the polymer one.
Yeah.
That is cool.
Mhm.
And then you are now closer to Italy. That is you are a definition of traveling scientist. I'm sure you have had a lot of research projects which are very, very interesting. So now this question is the one which I get the most hate for. So please don't hate me, Armando. If I ask you to pick one research project that you're most proud of, or the most fun and quirky
Mhm.
one, can you pick one research project from your journey as a scientist and explain it to us in simple words in the section we call In Other Words?
So after my master thesis, I started working with quantum dots and on different aspects of these quantum dots, and I kept working on this field since then because there is a lot of fun stuff to do. So conventional way of making quantum dots is relies on stress. So essentially, what you do is you start with a substrate material. So you have to imagine a crystal with a perfectly arranged set of atoms forming a lattice. You can imagine them like the squares of this piece of paper. And what you do is that you put on this substrate another material which would form also a crystal, and maybe the spacing between the lattice planes is different. And the usual way is to take a material which is slightly larger. So what happens is that when you start depositing this material, the first layers try to adapt their distance, their interatomic distance, to the underlying substrate. But to do so, there is elastic energy or stress piling up in this layer. And what the layer does to try to relax, because as we humans, we don't like to be stressed, so we like to be stressed for a while and then we want to relax. And the same thing happens for this material. So after a certain layer which is stressed, you have islands forming on this material, bumps, where the atoms try to get far away from the substrate which try to tell them how to arrange. So these atoms build up bumps, and these bumps allow the atoms to get farther away and get to their natural distance. Okay, then these bumps are covered with the same material as the substrate. Usually these bumps, you have to imagine these bumps, we were discussing about these portions of a sphere, they are covered with the same material as the substrate, but they still stress, okay? And this stress has some drawbacks. So when I started my postdoc, I was wondering if we could get dots without stress. But the question is not trivial because you need stress to create these dots, and these dots stay stressed. Okay, so in the first place, you need to find a way to make dots without stress. So without the driving force for making the dots. That's the question. This was the first thing I tried to do during my postdoc time in Stuttgart. So it was a very long day. I started at maybe at 9 in the morning, and I kept doing. I had this idea. I wanted to see if this works, and I have grown the samples. So I produce these samples and take them out from this oven, which is the molecular beam epitaxy, and then put them under the microscope, and then looked at them. At 6 in the morning of the day afterwards, I found the proof that they had created a new kind of quantum dots, and it was really exciting. So nobody was there around, but I called home my parents at 6 in the morning to Italy and saying, "Oh, I found something cool. I really like it." Then, it was a bit disappointing to see that nobody was caring much about that because it was kind of exotic, and whenever you do something new, people are skeptical, maybe it's something useless, and so on. It took many years, but people started getting interesting, and people started having new ideas on how to make these holes and how to fill them. And then we picked up those ideas, we continue developing them. And then it's very nice to see that after 20 years now, these quantum dots, which are without stress, are taking over the field because they have much better properties.
This is so cool. So you basically, talking about the science aspect of it, you basically did like a negative correction, so to say, that you knew that there's going to be a bump. That is how the quantum dots are happening with the stress. So what
Yeah,
you do is,
yeah,
instead of having like a flat-ish surface, you do like you make
right.
holes, so to say. When it will be stressed, then it will just rise up and it won't be a bump. Then it will just be, instead of having a hole of, let's say, 10 meter or 10 nanometer deep, it would be a 8 nanometer deep, something like that.
Well, it's not much about a matter of height. The question is the materials which you can combine. So in the stress quantum dots, you need to combine materials which have different lattice constant, and so the result will be a stress quantum dot. While in this new approach, or this alternative approach, which starts with a hole, you can fill whatever you want inside. Actually, you don't. It's better to use a material which has the same lattice constant as the substrate material, and then this will be unstressed.
It's mainly you're controlling or you're creating the quantum dots which are not stressed, like relaxed quantum dots. It's not about the
Right.
final product when we are doing this bump, lowered bump thingy, crest, or the trough, no, crest sort of a thing. It's more about when the materials are coming in contact to create these quantum dots. That, so for that condition is that is the key. Ooh. Oh, that is so cool. Okay, now I understand it even better. So it's like the, oh, oh.
But you have the same lattice constants. So there is a you can combine two materials which have the same size. That is constant. So the atoms have the same distances, and still have an object, a three-dimensional object, which behaves as a quantum dot.
Armando, this is so
So
cool.
that,
This is so cool.
I'm happy that you like it.
It's amazing, and I can totally imagine this. Coming back to the emotional aspect of it, that you started working like on a normal time, let's say 9 a.m. or something, and you did it and you did it and you did it and you did it, and then next day 6 a.m. is when you got the result, like the first proof of oh, I made it in the molecular beam epitaxy, and then probably under the microscope, haha, under the microscope. This is so cool, and this reminds me also of the first time. So when I was doing my master thesis at the same Max Planck in Stuttgart, probably we were in two different buildings and two different, of course, at two different times. So my master thesis was about growing graphene, twisted bilayer graphene with chemical vapor deposition. And it was in the clean room, the oven was in the clean room, and the process usually was taking 24 hours or 48 hours for the growth, because you're slowly growing it. And I was in the lab at like 6:30 or 7 in the morning, so to turn off the oven and to see, like, take the sample out and stuff. And there was no one else in the lab. Also, it was safe because there was no chemical reaction happening anymore. And it was the first time that I saw, with all that clean room suit and everything. I had the sample, which was like at 45-degree angle. It was a copper piece of copper, and it had these hexagons which were bright on it. And that was the first
Yeah,
time
great.
I created
Graphene.
graphene, which you could see with your naked eyes. And of course, I had to put it under the
Yeah,
microscope,
great,
electron microscope, do Raman to
great.
confirm it is monolayer and everything. But that was the first time, and there was no one around, and I was like, "Oh my god!" So I really had to go out of the lab, go to the this tiny lake that we have at the Max Planck campus in Stuttgart, and just breathe. Behind the building there is this tiny, not a lake, it's a pond, almost some water body, and that's where I had to go and be like,
Yes, yes,
yeah,
yes. I
and
know.
just
Yeah,
there
yeah.
was the bench,
Nice.
and I was like, finally it happened. So I totally understand that you called your parents like, hey, I got it, I got it, what I wanted. Your parents probably didn't know what to do.
Well, when they understood that it was
Exactly.
happy,
They're like,
surely
good
as
job,
all parents,
son.
they get happy as well.
That is so cool. And this was something that you did, let's say, what, 14 years, 30, more than 14 years ago.
Well, it was
20
20
years
years ago.
ago, see? And now is
It was
2003.
2003. Yeah.
Okay. This was before the graphene paper came out. That was in 2004.
Yes. Oh, about graphene, I have a story.
Tell
Sorry,
me, tell
maybe.
me. Graphene story.
Uh, yeah. During my PhD, I was doing STM, so scanning tunneling microscopy, in Zurich. And to calibrate the scanner, I had a piece of a pyroelectric
HOPG, yeah.
HOPG.
Yeah.
Yes. And actually, the standard way of calibrating STM was to look at the surface of graphite, and actually to get it clean, we had a piece of scotch and peeling off
Yes.
graphite. And I remember the moment where I did it the first time, and looking at what I peeled off. Oh, this looks really cool. I can peel off layers of this stuff. Okay, but let's calibrate the scanner. So throw away these things. And it was 2000. It was 2000.
Well, you threw away graphene, Armando.
I remember that I was curious
Uh-huh.
about that, but I was under pressure because I had to obtain results on my relatively boring compared to
Yeah.
graphene. Yeah, this was already standard, so it was the discovery of the scotch was okay. But the new thing was to look at what you peel
Exactly.
off.
I think this is the standard practice, right? You take a piece of graphite and then you exfoliate the top layer off so that it's like you get a clean surface for calibration. And this is so cool that, oh wow, that is so cool.
Well, I missed the Nobel Prize.
Yeah, well,
So,
you're working on cooler stuff now, so it's fine. But this is really cool. So you made graphene before without even realizing it. And just like you, many other
without
scientists
realizing it,
also probably
that's
made graphene without
yeah.
realizing it. That is so cool. Awesome. So this was your research project that you're super proud of. But of course, we are not playing favorites here or anything like that.
I must also say that many others, of course, contributed to the field, and the discovery is just on the way. So there are many ideas and many coincidences which must come together at the right time, the right
Absolutely,
place.
absolutely. So, Armando, it's very clear to me that the research aspect of being a scientist, being a professor, is really what drives you. But what else do you like about being a scientist?
I think so. The one of the aspects I like is the fact that if you're a scientist, you're allowed to a certain extent, to stay child all life and to keep playing. The difference is that you get more and more expensive toys to play with, and of course, as you grow up in science, what I like is to also to transmit my passion and my knowledge to students through teaching and also through supervision. And those are the things I like the most. And we have also quite much freedom. We have flexible working times usually, and that's nice. And also, a very important aspect is also that we get in touch with the international community. So we have colleagues everywhere in the world. So if you go to some place, there is a very good chance that you know people there, maybe in the US or in India or China or Brazil, and you get to know many people, many cultures.
Yeah, yeah, definitely. And that's why I think Doris also, she also mentioned this. She had this Science Bridges culture
Yes,
sticker, which
yes,
she
yes,
had on, like the pin on. No, absolutely, absolutely. And I completely agree with the expensive toys. The toys just get more and more expensive and more fun to play with. It's so much fun
yes,
to, it is so
right.
cool. And this is really, really important, right? Also the collaboration and international community. And the two examples of that are right behind you. If anyone is watching, there is the Quantour project, which is a quantum emitter's journey through Europe. And then there is the Quanta, which is Quantum Science Austria. So tell me a bit about Quanta and then tell me a bit more about Quantour.
Yeah, okay. Maybe I can start with Quante. So Quantum Science Austria is a new cluster of excellence in Austria. So it's funded by the FWF, the Austrian Science Funds. The mission of this project is to bring together all the scientific community working on quantum science and on different aspects of quantum science in Austria together. So the coordination is at the University of Innsbruck, and we, as the Johannes Kepler University of Linz, are part of this initiative. Then there is the Technical University of Vienna, the University of Vienna, the Academy of Sciences, and the IST Austria. So we have many people. So we have about 60 PIs, so 60 scientists, and they're all groups. So it's a very big community, very big family, working all together to push forward the frontiers of quantum science.
Austria, right? All of these 60 PIs or groups are in Austria. That is amazing. Sorry, go on.
Yeah. So actually, it's slightly different from the initiatives in Europe. So our focus is on fundamental science rather than technology, because there is no technological development or without fundamental science, and we want to make sure that fundamental science it keeps its momentum.
Yeah, you're absolutely right. I've only heard of these clusters of excellence. This is mainly in the tech transfer or spin-off sort of a space. But yeah, fundamental science also deserves clusters of excellence. So, okay, so the fundamental science, that is the focus. And of course, if there is the potential of tech transfer, of course, you will not be like, don't talk to us. Talk to us in 5 years.
No, of course not.
Okay, so this is like 60 PIs. Based only in Austria at the moment. Is it Quante or Quanta?
It's actually, we call it Quanta.
Okay, it's fun.
I think
it's Quanta. Okay.
It's Quanta.
Okay. It's Quanta.
I'm not sure. I think we usually say Quantum Science Austria.
It's Quanta. From now on, it's Quanta. It's done. It's official. No, I'm kidding. Okay, perfect. So 60 PIs in Austria. That is brilliant. That is the Quanta. What else did you want to tell me about the Quanta project? Oh, cluster of excellence. Yeah.
Yeah, of course, it's not an isolated project. So each of us is collaborating with people abroad. Of course, it's just part of the international efforts, but bundled, at least in Austria, we want to make it a hub for quantum science.
One-stop shop.
One-stop shop for quantum science, and of course. We are communicating with technology. So we know that quantum science can have applications, and we are open for that. So there is this interaction, of course, with technological oriented projects.
Okay, that is perfect.
If I move now from Quanta to Quantour, there's Quantour. So there it's more maybe towards technology. So we want to show there that we have a semiconductor-based source of quantum light, which could be used, for instance, for secure communication. And we want to show with this project that semiconductor-based light sources are stable. So this source is starting from Berlin, and then it's coming to Linz, and then we move across Europe and go back to Berlin, and then we want to show that this is still working. And we want to perform measurements at different stations and compare these measurements to see if they are compatible. Since there is no standardized measurement protocol so far, so that's the first step towards that.
Okay, that is really cool. And how has your experience been like with the contour, with the Q source? Tell me more about because also Doris joined the handover and everything. How was that? How was that like with all the celebration and the sticker ceremony and all of that? How was that experience? I mean, of course, I'm also interested in the science, but you probably don't want to talk about the science now because potentially this work will be published, or most probably this work will be published. But what was that experience like? Because you are the first contour hero from Berlin. You were the first stop.
It's an honor to be the first stop. Well, it has been a lot of fun up to now. So we picked up together with Maximilian Agner, a PhD student in my group. We picked up Doris and Lucas at the railway station in Linz, and then we went through the city center. We made a stop to take a picture, and then we came to the university. And Lucas and Maximilian wanted to load immediately the source in the cryostat and start measuring it. And so it has been a lot of fun. And actually, we had the occasion, just in the same week, we had a workshop. It's the second international workshop on gallium arsenide quantum dots. And so we took the source with us. We brought it to a very beautiful place here in Austria, which is Traunkirchen. It's a Traunsee with view on the Traunstein. Everything is Traun. The source went around also to some beautiful landscape here in Austria. And so up to now, it has been a lot of fun. So we made the sticker ceremony in Traunkirchen just last week. It was fun. Yeah. And I think we'll keep being fun in the future. So Maximilian looks forward to hand over the source to
the next contour hero, which we will not reveal who it is. But if you check out the website, you will know who the next contour hero is. So everyone watching, listening, if you're curious, go to thesciencetalk.com/contour and you will find all the heroes and everything there. That is really cool. Are you also already starting to get ready to say goodbye to the source, you and your team, or are you super attached to the source?
No, I think we have enough quantum dots. So usually we produce billions of them. So, but we are of course happy to have this one here, and so we look forward. So the mission is to let this source travel. So it's just a continuation of a trip. So it's not a final goodbye. We will keep seeing people around, and then the source perhaps we will visit one or the other of the colleagues. So.
That is a very grown-up answer, I have to say. A very grown-up answer.
Yes.
That is brilliant. That is brilliant. Perfect. So then let's shift gears and go back to your research experience as a whole. It sounds to me that your research experience has been wonderful. Of course, we only spoke for over an hour now. But if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here. 3 wishes, go.
Yeah, actually, I would have 1 wish, and that is that I find that that there is a lot of bureaucracy which is pulling the brakes on science. So to allow science to go on, what we do is to apply for projects and to get funding, both for the equipment and for consumables, but also most importantly to sustain the salaries of PhD students, to allow them to work and to create and to become the next generation of scientists to the benefit of our society and industry. And now this project application procedure, what I've seen over the last years is that it's getting more and more bureaucratical. So the formalities to apply for a project keep increasing, and so to say, the pain doesn't finish with the application of the project, but it continues during the course of the project, where we have to write reports, and then it's keeping increasing. So you keep having like formatting of CVs that must fulfill very specific guidelines and stuff like that, which has nothing to do with science. And all the time I spend, and my colleagues all the world or across Europe spend in doing these things, is time which is lost from our real job, which is to create new ideas and to train people, the next generation, which is a basis for the well-being, I think, in Europe. That's a big pity, and that's my wish that people,
Less bureaucracy.
yeah, that's bureaucracy, less bureaucracy, and give us back the time for the things we love and for the things we are trained to do.
Right. I understand that this challenge or this pain is so strong that you just want less bureaucracy, less bureaucracy, lesser bureaucracy, no bureaucracy. It's literally
Now
that.
that's well, of course there is need of course of certain rules and certain frameworks, but at this stage it's too much.
But Armando, this was your chance to put it out in the universe that you don't want any bureaucracy. This was your chance. And you went super realistic and was like, no, no, we actually need bureaucracy, just a little less.
No, well, there must be some of course some rules, but it's going too far. So the bureaucracy and science are diverging. So people seems not to understand each other anymore.
Yeah, and it's also right. I completely agree with you. This bureaucracy, it's important, but it's also it takes away from the fundamental, the core of your job and what you enjoy, and that just dampens the fun and kind of sucks the joy out of it in some cases.
Resources
And the resources, yeah, exactly. I hope that we will have lesser bureaucracy or better structures to support professors like you. Like I think we need to combine it both because it's like lesser bureaucracy, but
Yeah.
also in addition support for these kinds of bureaucratic tasks which you don't have to or you shouldn't have to do. But I'm confident that we have scientists like you who are aware of this and who are voicing it and who are also starting to become more and more decision makers in the system to change the system, so to say. So we will have lesser bureaucracy. The next generation of scientists will hopefully have lesser bureaucracy.
Hopefully.
Fingers crossed for that. Armando, this has been wonderful. I have learned so much. I have learned so much. It has been so much fun talking to you. But before I let you go, I have to ask you one last question, and that is about your time, your 1 week on the Real Scientist Nano Twitter account, or X account as we call it now. In addition to featuring as a guest on Under the Microscope podcast, every guest will also get the keys to the Real Scientist Nano Twitter account for an entire week. So, what can the followers, the more than 3,000 followers that we have on the Real Scientist Nano Twitter account, don't worry about the numbers. There's no one there, no one's listening. What is the plan? What can the followers expect in the week that you're taking over the Real Scientist Nano Twitter account?
Well, I think we will post pictures of our labs and short movies of what we are doing in the lab and of the city of Linz and the beautiful campus here in Linz and the surroundings. Yeah, this is and some surprise perhaps.
Oh, some surprise. So lots of beautiful pictures, lots of lab pictures and people pictures and the science as well. I want to see the SEM images of those bumps. I want to see everything.
Okay.
I want to see everything.
We'll do that.
Alrighty, perfect. And lots of pictures with the source of the Quanta source, the Q source.
Of course.
Yeah, that would be awesome. Perfect. Then thank you very much, Armando. This has been
Thanks
wonderful.
you,
and excited to have you now on Real Scientist Now. Thank you.